Yeah, now let's continue from where I have ended in the previous video. Coming to my next slide, which is improvement proposal by part 6. Like in this part of project, like mainly that I have focused on improving the performances of CNN on the C410 dataset. Like as we saw earlier, the baseline model worked. It was a bit and which has a like very limited limit by accurating 70% with no further improvement. For this, the main reason was that it was too lagged regularization with shallow. So in this improvement phase, where we have implemented and tried several key changes. Basically, the the first which I have added a third convolutional by pooling block with 128 filters by giving more filters which helps the capture deeper to network with more detailed features which things like complex structures, color gradients, the main features, things like complex textures or the color gradients and edges which may appear in real old images. Coming in second, that where I have introduced the batch normalization after every convolutional layer because this step helps by stabilizing and speeding up the training process by normalizing all the activations. With that, it had prevented exploding by vanishing gradients, and this has helped me the model to converge smoothly. And coming to third, where I have included data augmentation with random horizontal flips and random grouping of images because these images had been horizontal with augmentation so that I have to make the network more robust because it does to learn to recognize an object even when its position or orientation changes slightly or moderately or highly because this recognition of an object or robust so much. And lastly, I have reduced the learning grade to 0.0005 by a smaller learning rate ensures to convergence of smoother and it has prevented the optimization from overshooting the minima during all the training. All these enhancements which I have aimed to make the model generate the better, reduce overfitting by ultimately performing so well with more consistently on the unseen test data because this unseen test data adjustments are aimed to improve to a future generation and reduce overfitting. Uh, Here I have inserted this normalization for the each convolution layer to include the random flips and the crops. With that, we continued using the softmax cross entropy laws and optimizers of Adam. And coming to next slide, where we have improved the CNN, the design. This design, like it visualizations, approved from all the CNN structures, looks after those changes. The changes is given over the. Let's go to the all the heads of which they have given. Let I have compared here five numericals with layer of type with parameters and with the enhancements. With these enhancements, I have done all the convolution plus full maxen by batch norm and real evolution. After all this, the CNN to build hierarchical features from simple edges in the first layer to more abstract patterns in the further layers or the later layers because the first step just it starts to complete with the clarification to end up to the last layer. After all these convolution layers, we still have a fully connected layer with 1024 neurons and RLU activation with proper to prevent our overfitting. Because this because the C4 10 are giving less approximately values of 70% when compared to other one, because it has been giving 74% at 1400 steps approximately. At adjacent point, I guess it is 1420 or 1470 maybe. So with that, all the 10 classes correspondence of the cipher 10 data types. Let's take in terms of flow. This data moves from convolution to pooling, then through deeper feature extraction before it dense layer to passed by being flattened. By introducing the batch normalization, depth and the additional, the model became more stable and capable of learning with all the spatial relations between the every pixel, because the pixels gives a range of each point to point. By overall, by designing the network more powerful pixels. And coming to next slide, of which we have results of improved of each model. This slide shows like how we have improved during our training by progression of accuracy over time in every step. Like as I've told, like at every step 100, it has shown the 19% accuracy, which is normal since it was just beginning to learn, because at the end it may increase or it can stay in between. But I guess as per at step 4, step 3, I think it may reach to high. Let's take by step 1000, like where which accuracy model 45%. And coming to the step 3, where the 3000 steps have reached to 53% by showing steady learning, because it is gradually increasing from step 100 to 1000 and from 1000 to 3000. And as I have told, it may reach higher in the middle case or the final, but on an average or approximately it may reach to low at the final when compared to middle of the region, because at middle it shows more. And then it peaked about 66% around the step 4600. By step 6000, the accuracy stabilized near 60%. Now let's take the interpretation of how this has happened, like what's happening. Like let's take interesting the facts that we're gonna talk here, which is the interesting here is not the accuracy percentage but the training stability. The graph showed smoother with more controlled growth with fewer fluctuations, because at every step it has been increasing. When comparing to the fifth and sixth, it has been high, at the final it has been low. So these are the fewer fluctuations that we have done here. The stability came from the batch normalization, which helped the layers maintain consistent activations to growing from 1 to n. Also, with the data augmentation, the model generator helped followed by giving better, but it didn't give any memorizer training to data and accuracy, all the steps to set the always closer to the training accuracy. Like the model generation slightly better on unseen data, because the improved CNN learned more efficient by avoiding overfitting, and it has produced more stability results. The final accuracy didn't stood dramatically higher, because as I've told at the step 4600, it has peaked to 66%. But overall, the learning behavior became much reliable on each step. Coming to next slide, let's compare our summary to the each model with data set and accuracies, and with the comment where this slide generally summarizes the differences between the baseline and the improved model, because the baseline CNN, the computer network convolution neural network, had two convolution layers by achieving around 70% accuracy. But instability, it has showed unclear signs of overfitting. By improving CNN, added an extra convolution layer, because we have used the batch normalization and data augmentation, so that it can reach about 62% to 66%, where the 66% has accuracy with better stability and generalization. And let's take our key takeaways. Because the deeper networks are much better at handling complex data like C410, which it abstract features like shallow model. And the C410's performance is limited not by the algorithm, because it may varies in size with high variability, or it can reach from high to low, because it has reached a point to high around 4000, around 4600 step, because it has done the batch normalization, like it has played a major key role in keeping learning steady. And by doing all this together, like the improvements which they have shown are taken moderate architecture by changing make a CNN significantly more dependable. Even it may doesn't skyrocket accurately headline, because this normalization and augmentation help maintain to steady learning of deeper networks to complex our minimal data to cipher performance, which it can changes its variability from size from or to data set of variabilities. Now coming to the conclusion of, I can say that like let's look at the key conclusions of this entire experiment, like what we have learned or from beginning to the end. I felt like from beginning to end there has been much there has been much numerical comparisons and images comparison. Like for the effectiveness of CNN strongly depends on datasets complexity. Like let's take an example, like where an NFT, which is very simple, can reach nearly perfect accuracy with even a very small model. But the Cipher 10 isn't like that, because these images and it occupies and it takes many pixels when compared to MNAST. Like here we have used the real world color images. Maybe that's the reason, because it has taking more pixels. Like where it has needed a deeper and more rigorous network to perform well. And secondly, this MNST can achieve near perfect accuracy with both batch normalization and data augmentation. It significantly enhances models' robustness by giving stable gradient flow. Like this data augmentation helps generalize to beyond the data of training, because of this network depth regularization so essential to tackling complex visual patterns. A CNN that works for a grayscale digits, because it works on the digits. That's the reason this MNHT has accurated so highly when compared to C410. So here by using our TensorFlow levels of APIs, it has given our overall control by building and training a different or how the model was built and trained, and it provided deeper understanding of how every layer has been operated effectively. So here to TensorFlow, to conclude this project, maybe demonstrated that CNN design is all about balance, because it has involved in all the depth regularization and data diversity when we have used correctly. Because if you use any any picture, it has give to perform reliably even on challenging data sets like C410. Yeah, as we have understood, this C410 has occupied more pixels when, because it is not even digits, right? So here by concluding, I say that this, to wrap up this, like let's say this project wasn't just about achieving like what you have done to gain or to understand what we have done here. It's just about achieving our higher accuracy. It was about understanding how every layer, every parameter, and every adjustment that we have made affects the overall model performance.